Momentum and Impulse Lab by Indiana Jones, Jesse McCassidy, Dean Henderson, Terdium Aquilium, and Chris Pratt. The goals of the labs were to prove the law of conservation of momentum and the impulse theorems. The law of conservation of momentum states that the net momentum in a system is constant before and after a collision. So the momentum of object 1 plus the momentum of object 2 initial is equal to the final momentum of object 1 plus the final momentum of object 2. And the impulse theorem says that an impulse or external force is equal to the system's change in momentum. So we'll prove these by analyzing 4 different types of collisions: inelastic collisions, perfectly inelastic collisions, elastic collisions, and explosions. And we'll prove the impulse theorem by using a force probe and one of the cards. All right, so a perfectly inelastic collision is a collision where 2 objects come together and tend to stick together and move in one direction. So the formula for a perfectly inelastic collision is the momentum of object A initial plus the momentum of object B initial equals the momentum final of the whole system.
Partially inelastic collisions. This is also known as the most common type of collisions, and a most common example of this collision is 2 cars colliding on the road. And since it is partially inelastic, that means it is not like perfectly inelastic collisions in the sense where the objects do not stick together after they collide. Therefore, the 2 ending velocities of the different objects could be different. And so we're still going to use the equation from the law of conservation of momentum, which is the impulse of object A plus the impulse of object B equals the initial of those 2 equals the impulse final of object A plus the impulse final on object B. And since we know impulse is equal to mass times velocity, we could say that the mass of object A times the velocity of object A, all initial, plus the mass of object B plus the velocity of object B, all initial, equals the mass of object A times the velocity of object A final equals the mass of object B times the velocity of object B, all final. And so this type of collision is when 2 objects collide together and then move on away from each other at either different or same speeds depending on your numbers. And so once you plug all of your numbers in, the number should be the same of impulse since no energy is lost, and this equation holds true due to the conservation of momentum. And below you can see our work in the lab when we recorded the velocities initial times the velocities final, which we do not have mass involved because the masses are the same, therefore they can be canceled out. And then our equation on the right, which shows them not exactly equal, but this is due to human error and not the law of conservation of momentum being incorrect, which is human error in the lab. And so this type of collision is partially inelastic. And since it is a partially inelastic collision and the objects do not stick together, kinetic energy is not conserved. So a portion of this energy is lost through ways such as sound, thermal potential energy, and other types. So the kinetic energy does not stay the same, which is why when you drop a ball on the ground, it does not come back up to the same height as from where you dropped it from, because kinetic energy is lost throughout this collision.
Another one of the 4 types of collision related to momentum is the elastic collision. An elastic collision is a collision or an encounter between 2 bodies where the total momentum or the total kinetic energy between the 2 bodies remains constant before and after the collision. In some scenarios, this collision can be described as the most bouncy, and it differs from a perfectly inelastic collision as the two objects bounce off of each other, or one object bounces off of another object, rather than the two objects sticking together after the encounter. Nonetheless, the total kinetic energy is kept constant before and after the encounter. One example of an elastic collision would be a ball bouncing off a wall, while maintaining the same kinetic energy before and after the ball bounces off the wall. Another example would be in baseball, where a pitcher pitches a ball and a batter bats it back. The ball, before hitting the bat, has the same momentum as it does after hitting the bat. Now, in relation to our experiment, we had two carts traveling at different velocities which collided with each other, and then traveled away from each other at, again, different velocities. However, if you add up the momentum of the two carts before and after the collision, you will find that they equal each other. This also means that they had the same kinetic energy before and after the collision, which is a proof of the law of the conservation of momentum. The fourth and final type of collision relating to momentum is an explosion. An explosion is a specific type of collision, yet still relates back to the law of conservation of momentum. In an explosive collision, two objects contain the same initial momentum before the reaction. In most scenarios, this is zero, or the two objects remain stationary before the collision occurs. However, once a reaction occurs, the two objects collide and explode away from each other in an outwards direction. One example of an explosive collision would be a cannonball shot from a cannon. In this scenario, a cannonball is shot at a very fast velocity away from the cannon. The cannon itself recoils a little bit, but not a fraction of the distance which the cannonball would travel. This makes sense because if you look at the equation of the law of conservation of momentum, momentum is equal to mass times velocity. So it makes sense that the cannon does not recoil the same distance that the cannonball travels because the cannon has a significantly greater mass than the cannonball would have, and the cannonball travels at a much faster velocity than the cannon would. Nonetheless, the momentum of the two objects before and after the collision are the same. In a similar scenario, when a bullet is fired from a gun, a similar reaction occurs, and the bullet is fired at a very fast velocity away from the gun. Again, the gun would recoil a little bit, but not nearly the same distance that the bullet would travel. However, the gun would have a much greater mass than the bullet. Therefore, the momentums, again, before and after the collisions are equal. Now, in relation to our experiment, we had two carts that were stationary in the middle of the track, with one spring loaded facing towards the other cart. We would set off the spring, and the two carts would explode away from each other. In the picture in the slide, you can see that the initial velocity of both carts was 0 meters per second. After the explosion occurred, the velocity of the first cart was 0.245 meters per second, and the velocity of the second cart was negative 0.237. In a perfect scenario, these velocities would be equal. However, they were very close in our case. It should be noted that one of the velocities was positive and one of the velocities was negative, because one was traveling in the positive x direction and one was traveling the negative x direction. Nonetheless, they cancel out, therefore proving the law of the conservation of momentum.
In the second half of our experiment, we are trying to prove the impulse momentum theorem, which states that the change of momentum is equal to the impulse applied on the object. Impulse is basically a force, so the force is equal to the final momentum minus its initial momentum. To do this, we design an experiment where a car on a relatively frictionless track starts at a velocity of 0, so that also means the initial momentum is 0, and then a plunger is pushed and that force is recorded using a force probe, and then its velocity is recorded using a motion detector and a lab quest. After this, we would use the trace feature to find the slope of our distance over time graph, which gives us the velocity that the car was moving at. And then we found the area under the curve from the force probe to get the total amount of force applied on the object. So from there, we calculated the velocity times the mass, which was 0.25 kilograms, and we compared that to the force, and then we plotted them on a graph as the x-axis being the change in momentum and the y-axis being the impulse, which should have a slope of 1, considering they should be equal. And these are the equations which we used in our calculations. The top three are just different forms of the law of conservation of momentum. The top one saying the final momentum of A plus the final momentum of B is equal to the initial momentum of A plus the initial momentum of B. The bottom one is saying the exact same thing, but just using the definition of momentum, which is actually the equation we see at the bottom. And then the other one is the most simple form, which is just the final momentum is equal to the initial momentum. The equation on the right is the impulse momentum theorem, which is the change in momentum is equal to the net force over the change in time. And these are our results. The graph on the left is the data from the impulse momentum theorem, in which the x-axis is the force applied over the change in time, and our y-axis is our change in momentum. We got a slope of 0.875, which calculates a percent error of about 12.5%. We were expecting a slope of 1, as the change in the x-axis should be equal to the change in y-axis, since the change in force applied over delta t should be equal to the change in momentum. So we got a decent bit of percent error. Some possible sources of error could be some friction when we were pushing the plug down, which took away velocity from the car, we also could possibly just have a sloped track, and it was causing it to slow down or speed up faster than we would have expected. The graph on the right is from the law of conservation of momentum portion of our experiment, in which our x-axis is our initial momentum and the y-axis is our final momentum. In this, we got a slope of 0.995, which calculates to 0.5% error, since we were expecting a slope of 1 for similar reasons, that the initial momentum should equal the final momentum based on the law of conservation of momentum. Some possible sources of error in this could have been, again, a missloped track, or some, for the explosions, again, the friction from pushing the plunger down to moving outward. We could have had issues with the magnets in the cars being attracted to the magnets on the station. Although in the end, it seemed to work out pretty well, as we had a low percent error.
Overall, after completing this lab, we believe that we designed well-developed experiments to test the law of conservation of momentum as well as the impulse momentum theorem. When taking a look at our results for our law of conservation of momentum lab specifically, you can see that we have a percent error of 0.5. This is depicted on our graph with a slope of 0.9947. This slope can be compared to a slope of 1, which would have been perfectly accurate data. Similarly, for our impulse momentum theorem lab, we have a percent error of 12.5 with a slope of 0.8752. Again, this can be compared to a slope of 1, which would have been completely accurate data. In our lab where we tested the law of conservation of momentum, we tested all 4 collisions 3 times for a total of 12 trials. For each trial, we calculated the initial and final momentums of both carts using a motion sensor and linearized our data, which you can see in the graphs and the results. For the impulse momentum theorem lab, we found the initial velocity and the final velocity, as well as the impulse for the carts over 10 different trials. For this lab, we use motion sensors and force probe devices to calculate our data, which is again linearized and represented on a graph in the results section of our presentation.
The end.